This is Ming-Chang Yang from the Chinese University of Hong Kong. So I'm very happy to have this chance to be here to share some of our thoughts and our recent research results in this RISC-V online bootcamp. Okay, so although that we didn't having some direct output relevant to the RISC-V, but I would like to propose some interesting intersection between RISC-V and my research area and trying to encourage more possible researches in this area. Okay, so we are a research team in CUHK are doing memory and storage researches. Okay, so here is our lab members. So right now we are having 5 PhD students and 1 MPhil students in my group. Okay, so they're all focused on different system research regarding either memory or storage. Okay, so that's also the name. That's also the key reason why I make the name of my lab like a memory and storage system math lab. So when we talk about the emerging memory or storage technologies, okay, so we can think from this memory hierarchy. So I assume that most of us are pretty familiar with this picture, okay. So as you can see in the left-hand side of this slide, in the so-called conventional memory hierarchy, we are actually having different layers of memory technologies, and they are trying to build the whole memory system as a pyramid. Okay, so just like we are having flip-flop as the CPU registers, we are having the static random access memory for the CPU cache, and for the main memory, we are having the dynamic random access memory. And for the permanent secondary storage, I believe that the hard disk have already dominated this market for many decades. Okay, but thanks to the quick advancement of different technologies, we are actually having a variety of different options, okay, to construct this memory hierarchy. So for example, we are having memory stir or different magnetic RAM like STT-RAM or SOT-RAM to replace the CPU register or the cache in the CPU. And we also having some like resistive RAM, fast change memory, PCM, or restrict memory to substitute the main memory. Okay, so even for the secondary storage, we also having quite a different options like PCM or even flash memory or even some next generation hard disk technology like the shingled magnetic recording or the interlaced magnetic recording HDD. Okay, so here I'm not trying to bore you because of these terms. Okay, I'm just trying to point out that thanks to the quick advancement from many fields, we are actually having different choices to construct our future memory hierarchy. Okay, and for this new memory technologies I just mentioned, they are having a quite different features compared to the convention volatile memory. Okay, that means this memory, they can all deliver so-called non-volatile capability. So they can retain your data even after the power cycling or power failures. Okay, so we can keep the data for a pretty long time, just like we can put our data in the hard disk for very reliability. Okay. So with this emerging memory technologies, they also encourage and inspire quite a number of different research topics, like for the non-volatile register or SRAM, people are still thinking to do so-called non-volatile processor. Because right now, our data can keep in the CPU for a long time, even after the power failure or power cycling. So people are thinking about, can we do the normally off computer? So we don't actually need to power off our computer thanks to this non-volatile capability. Or can we do so-called quick hibernation or quick restore? So we can actually turn on our computer in an instant. Okay, and people also think about, because we need to keeping the computer on. So can we do better energy harvesting for this non-volatile processor? Okay. And with the non-volatile main memory, people are also thinking about, can we do in-memory computing or neuromorphic computing? And even for some large-scale storage topic, people are also look into these new memory technologies or storage technologies to build different architecture, file system, or different key value store. Okay. But because today our topic should be relevant to the RISC-V, so I would like to focus the main memory part in this area. Okay. So besides of the non-volatile capability I just mentioned, this memory technology can actually provide us some interesting and promising features or new capabilities. Okay, so I'm going to show you in the coming few slides. So what we can have with this emerging memory is like, we can do computation near or in memory. Just like the Micron, they proposed this hybrid memory cube. They are like the pioneer to do this computation near memory. So they are trying to put an extra logic, okay, very close to the memory. They are actually tightly coupled together, okay, so that when we are like to do some computation, we don't need to constantly migrate the data from the memory all the way up to the CPU. We can do some computation very close to the data where they stored. Okay, so that's why some people also call it like near data processing. Okay, so it's actually enabled by the new memory technology. And another example I want to show you and share with you is about the resistive RAM or ReRAM. With the ReRAM technology and some well-designed innovative peripheral circuitry, they can actually do vertex matrix multiplication inside the ReRAM. So they just simply apply different voltage to different bit line or word line, and they let the current go through these memory cells. Then the vector matrix multiplication can be complete. So here I'm trying to show you that with the emerging technology, we can do actually more things than we think. So we can do computation near or in memory. So another thing is with the emerging racetrack memory, we can even do operation in memory. Okay, so here I shows you two different types of racetrack memory. One is the domain wall memory, and the other is Skyrmian racetrack memory. So as we can see in the below figure, they are quite different from those existing like SRAM or DRAM. They are mainly cell-based. That is, each bit of data is keeping in a memory cell. But in the emerging racetrack memory technology, they are trying to trying to accommodate a bunch of data along a long track that is called racetrack. So that's why they make the name as racetrack memory. So they're having quite different and very interesting property. Like if you apply the current to the racetrack, you can actually shift. You can move along with the track. Okay. So here I show you some toy animation for like I'm showing you how we can move the domain wall data or the Skyrmian-based data along the racetrack. Okay, so that's the thing we cannot do with the traditional memory. And another promising feature that is brought by the Skyrmian racetrack memory, that we can even do this kind of in-place data update. That is also cannot be done using the conventional memory technologies. So for example, we can easily to update a certain bit, okay, directly in an in-place way. And we can also delete a bit or even insert a bit. So you can see the racetrack memory, especially the Skirmian version, they're actually highly operational. So you can see the researchers in this area start to think about quite different data manipulation or different data operation. They are thinking about how we can manipulate this data along the racetrack so that we can deliver more efficient computation or deliver more faster memory access. Okay. So using these two general example, I'm trying to convince you that for the people in the memory community, we are thinking not only using memory. We are not thinking about just accessing memory. We're also thinking about, can we do something more intelligent? Like, can we do computation? Can we do some more complicated operation near or just inside the memory? Okay. Okay, so, but even though there are a bunch of very excellent research has been proposed, but the fact is that what we have in our current ecosystem is that we only having this low store architecture to access our memory. So for example, RISC-V also adopts the low store architecture. That is, we can only do the arithmetic instruction. Okay, we can only use then on the CPU register. We are not able to do these arithmetics or computations on this memory directly. Okay, instead, we can only costly load or store the data from memory to processor or from the processor to memory so that we can do the arithmetic instructions. Okay, so even though I'm showing you that we could having some very promising and interesting capabilities using this emerging memory, but there are still having a very huge gap between this emerging capability and the existing architecture design. That is, we only have this low store architecture. Okay. Okay, so that's this big gap between the existing architecture or ISA and the memory capability strike us a new idea. So we are thinking about, can we try to extend the RISC-V ISA with some new memory instructions so that we can best utilize these promising capabilities enabled by the emerging memory technologies. Okay, so we are trying to propose this as a new direction or the new research area for study. Okay, so that would be our new attempt. We are thinking about, can we leverage the RISC-V ISA by extending it with some new memory instructions so that we can easily do the computation in memory, so that we can do some smart operation in memory, and we can still doing some system design space exploration on the existing full system simulator. Okay. So we are thinking that the RISC-V, we figure out that it could be the best platform to do this attempt. That is because the strong community in RISC-V, many people are thinking about how to support the RISC-V in several well-studied full system simulator like Gen5. So people in the big community think about, can we just build a more open source and more complete ecosystem by leveraging the RISC-V in the Gen5. Okay, and we also figure out that the RISC-V actually provides some customization capability or flexibility to define the new instructions. Okay, but I'm thinking that there's still few people to thinking about how to define new memory instructions and to leverage these emerging memory technologies. Okay, so In short, we are thinking that it's very interesting and it's valuable to see the intersection among the RISC-V, especially with the ISA extension and the emerging memory technology and the full system simulator, so that we can actually explore the system implication that could bring by these emerging memory technologies. Okay. So I'm trying to say how the RISC-V could also facilitate and ease some research topics in the community of the memory and storage people. Okay. So in the following, in order to let you better understand how the emerging memory could bring us some intelligent operation. So I would like to invite one of my PhD students, okay, Mr. Yang Zunyu, to present our recent research paper published in DEC this year. Okay, so let me welcome Mr. Yang Zunyu for the following sharing. Okay, thanks.
Okay, so thanks for my supervisor's introduction. And hello everyone, so my name is Chun Yang, and for the next part I will talk about one of our work, which is the permutation write, optimizing write performance and energy for the Skyrmian virtual memory. And this paper is published to the DEC 2020. And this is today's outline. So first of all, I will give the introduction and the background knowledge about the Skyrmian virtual memory. And next, we will talk about the design of the permutation algorithm, which leverage the special feature of this new memory technology to optimize the write performance. After that, system-level evaluation will show the effectiveness of the proposed strategy. And finally, the future work will be given and discussed. So the virtual memory is a new type of non-volatile memory technology with several promising features. For example, it can provide a high-density storage capacity like the hard disk, and it can also offer the efficiency rewrite performance like the DRAM. But most importantly, that it has a very special feature that is different from the other old memory technology. That is, it can use the current to shift the data along the racetrack. And right now, there are two types of the virtual memory. The first one is called the domain wall virtual memory, and it's a first generation. It suffers from the great challenges of reducing the domain wall size and the critical current density of the domain wall motions. And the second one is our main topic today, which is the Skyrmian virtual memory. And compared with the domain wall, it's more energy saving and has higher stability. So it's actually getting more and more attention. And this slide shows the basic structure of the Skyrmian virtual memory. We can see from the figure A that we have a racetrack and there are several Skyrmians on that racetrack. And the racetrack can be partitioned into several equal-sized bit zones. If the bit zone contains a Skyrmians, then we say that bit is 1. Otherwise, if the bit zone is empty, then we say that bit is 0. And in this basic structure, we need an injector for the Skyrmian creation and a detector for the Skyrmian detection. Besides that, we will also need a cross-shaped racetrack with 4 terminals for the Skyrmian's motions, and we will talk about this later. Also, please note that we often call the intersective bit zone as access port, because we can read and write data through that bit zone. So given this basic structure, we can define 4 basic operations. The first one is the detect operations, which is equivalent to the read. It can detect whether there's a Skyrmians at the access port. The second operation is the shift operation. By injecting a current between 2 terminals, the Skyrmians will be shifted along the direction of the current. And the figure B shows the example. We can see that if we inject a current from the right terminal to the out terminal, then the Skyrmians on the right-hand side will be shifted to left by 1 bit. The third one is the remove operation, which is equivalent to the write 0. We can see in the figure C, if there is an Skyrmians at the access port, we can give a remove operation to shift that Skyrmians out from the racetrack. The final one is the inject operation, which is equivalent to the write 1. And this is the most complicated operation since it contains 2 steps. The first step is to create a new Skyrmians from the injector, and then it will shift that Skyrmians into the racetrack. And there's one main challenge of the Skyrmian memory, that is, it suffers from high overhead when writing the new data, just like other NVM technologies, especially when injecting new Skyrmians to the racetrack. So naively write the data to the racetrack could trigger high overhead. And the right figure shows an example that uses a naive way to write a new data word. It contains two steps. The first one is it needs to remove all the existing skirmings from the racetrack, and then it will inject the new skirmings and shift that to form the new data word. So we can see that in this example, the number of the injections is equal to the number of 1 in the new data word, which is 4. And in fact, there were already some famous works for the NVM write reduction. One of them is the DCW, which stands for the data comparison write. The DCW will compare the contents between the old and the new data words before writing. So it can only update the bits when the corresponding bit value are opposite in both words. And frequent write is another famous design. It inherits the design of DCW. That is, you will also compare the content, but it can further improve the performance by introducing a single flip bit to bound the total number of bit updates. If the flip bit is set, then every bit will be interpreted as its opposite value. Otherwise, every bit will be interpreted normally. So by doing this way, it can make sure that its number of bit update will be always less than half of the word size. However, both the DCW and the frequent write are developed based on the cell-based NVM, just like the below figure shows. In the cell-based NVM, we cannot move the data. Because of this, the method is mainly based on the bit-by-bit comparison. So in this example, we can see that the first bit of this cell-based NVM is 1. Then we cannot move this value 1 to any other location. It has to stay at the first bit location. As a result, the bit-by-bit comparison might be the most effective way for this cell-based NVM. But this technology might overlook the topologically protected and the particle-like feature of the skirming racetrack memory. So the permutation write strategy is proposed to exploit these unique features. So different from the old method that the PW doesn't focus on the write reduction, but the injection reduction. Because the skirming injection is the most expensive operation. And the PW minimize the number of the injection by reusing the existing skirmings to form the new data. So instead of the bit-by-bit comparison, that the PW focus on the total number of the skirmings on the racetrack. And here shows the main idea of the permutation write. We can see that the first step is to assemble all the skirmings in the old data to the assemble area. Then it will permute those assembled skirmings to form the new data without a skirmings injection. We can see that in this example, because the number of the 1 of old data is equal to the number of 1 of the new data. So it will require no skirming injection in this example. And our PW strategy is developed based on this word-based structure for the skirming racetrack memory. Because our design mainly treats the skirming racetrack memory as a promising replacement of a memory, and the modern CPU usually access the memory content in the unit of a word. That is like 32 bits or the 64 bits. So in this word-based structure, that every word is associated with one access port for its data rewrite. And they will use the space of the right word to be the assembled area. And the following shows the details of the proposed algorithm. In general, that the PW algorithm can be divided into 3 steps. The first step is to assemble the old skirmings. That is just like the below figure shows. Whenever a new data word is written to the word W, that the PW will first count the old skirmings and then assemble them to their assemble area, which is allocated at the word W+1. Then the second step is to permute the assembled skirmings to form the new data word. If the assembled skirmings is not enough, then the PW algorithm will inject the new skirmings. But in this example, we can see that there is still one excess skirmings in the assembled area. So if this situation happens, then the PW algorithm will perform the step 3. And the step 3 is that it will remove all the excess skirmings in the assembled area. And because there's only one excess skirming in this example, so that skirmings will be removed in this step. And to better evaluate the PW algorithm, given the old data word and the new data word, we can construct an analysis table to summarize the cost of different write strategy in terms of the number of the 4 basic operations, and which is the shift, detect, remove, and the inject operations. But this part contains too many details, so I will skip this part in this presentation. But this analysis is well discussed in the paper. So if you're interested, please check out the paper for further details. So we compare our permutation right algorithm against the naive, DCW, and the flipping right. And the evaluation data set that we use is the MyBench. Here, please to know that since the skirmish memory is still maturing, so instead of showing the real value, we tend to measure the operational cost. We tend to measure the operational cost for each evaluated strategy. So we develop an in-house trace-driven simulator to model the work-based structure of the skirmish memory and measure the operational cost. And here shows our experimental result that there are 6 workloads here. And the x-axis is the 4 basic operations, and the y-axis is the number of the required operations. First of all, we can see that under all workload, the number of the ship operations are all very close to each other. Secondly, although the naive require a 0 detect operation, but it will always require 64 remove operation whenever writing a new data word. And on the other hand, although the other 3 write strategy needs 64 detect operation, the number of the remove operation is quite small. So the trade-off between the cost of the detect and the remove operations makes none of this write strategy has an obvious advantage in these 2 operations. As for the most expensive injection, we can see that the PW algorithm improved a lot in all the experiments. We can see that in the blowfish workload, which is the base case for the permutation right algorithm, PW can reduce the number of the injection by around 95.2% when compared with naive, and reduce the number by around 79.1% when compared with the flipping right. And even in the worst case, which is the Patricia workload, PW can still reduce the number by around 78% when compared with naive, and reduce the number by around 30% when compared with the flipping right. So on average, that the PW can reduce the number of the injection by 86%, 54%, and 49% when compared with the naive, DCW, and the flipping right respectively. And if we apply the real value, then the PW can improve by almost 35% in latency and 85% in latency when compared with the naive method, and improve almost 8.5% in latency and 21.6% in energy when compared with the other 2 advanced write strategies. But the permutation write strategy is not the only work that utilizes the special shifting feature of the skirmish virtual memory to do the optimization. In fact, another paper that published in the DEC 2019 also leveraged this special feature. And this work is called Zuma. To be more specific, it presents a relay architecture to enable efficiency random insertion and random deletion of large data. But different applications tend to have different data patterns. So in order to fully exploit the benefits of the PW or the Zuma, the programmer should modify several configurations so that they can meet their requirements. For example, they can set a different word size in the permutation right algorithm. So that's the main reason that we believe it's valuable to extend the RISC-V instruction set to support the new functionality of the emerging memory technology, so that the programmers could have enough flexibility to do their best optimization. And that's all my presentation here, and thank you for your attention.